the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is for linear algebra students who have already gone through kind of a review of systems of linear equations, solutions to systems, whether a system's consistent or inconsistent, row reduction techniques like the row reduction algorithm, some content on existence and uniqueness, and some knowledge about vector equations. This content right now starts into a whole discussion about matrix equations. So it's very important that you have already seen vector equations involving vectors, and we'll see them again here, but I just want to go ahead and take a moment to showcase a vector equation. Now, what you're looking at with this equation, as I said, you should probably already know this, but whenever I write down these a sub 1 vectors, a sub 2 vectors, all the way to a sub n, those vectors are actually the column vectors in the matrix A. And x sub 1, x sub 2, all the way to x sub n, those are the coefficients of those column vectors. They're also known as the weights for the linear combination of these vectors, and this is just a right-hand side vector we're calling B. Well, now we're going to dive into not exactly a matrix equation, because that's going to take a little bit of pre-work to get there, but how do you multiply a matrix and a vector? That's going to be very important as we move forward. So you need to know how to do that multiplication before we can define a matrix equation rigorously. So here's the definition, and it is a definition for matrix vector multiplication. This is just how it was decided a matrix times a vector should be. If the matrix A is m by n, and that's going to be very important, remember m rows, n columns, and if the columns of that matrix are, as I said before, a sub 1, a sub 2, all the way through a sub n, those are all column vectors in the space Rm. Now that is very important. Why is that statement important? Well, remember, A is an m by n matrix, which means that it has m rows. There are m of these rows. So each column vector had better have m entries. And that's why each column vector, it belongs to Rm. And I had somebody in one of my classes actually say, you know, that weird looking R, so that you can call that the real number system, or Rm, or you can say it's R double bar, because that's generally how it is written, is R double bar, like that. So this is R double bar M or Rm, whichever you prefer. Anyhow, so if we know that these A1 through AN are in Rm. Oh, by the way, I should also mention it's A1 all the way up to AN because, well, you have n columns. So you need n of those column vectors, and each of those column vectors has m entries. There you go. And that's why knowing the dimension of the matrix you're working with is very important when you're writing all this stuff down. So let's suppose that that condition is true. And if we also suppose that the vector x is a vector, x1, x2, all the way to x sub n, and that is in Rn. So it has n elements. Then we define the product of A, the matrix, and x, the vector, to be the linear combination of the columns of A using the corresponding entries in X as weights. Now that should sound very familiar because that is very close to what we used as a linear combination of vectors definition. Symbolically, it looks like this. And notice the order here. The matrix A times the vector X. It is the matrix on the left-hand side, the vector X on the right-hand side. It turns out the other way is ill-defined. We'll get to why later on. Well, the matrix A has n columns. Remember, A is m by n. So there should be n columns. 1, 2, ... all the way to n of them. And it should have m rows. Luckily, again, each one of these column vectors has m entries. So this fits so far. That's our matrix A, and there's our vector, column vector X. Notice it's nice and written out as a column vector. I didn't even write that actually as a vector. I didn't write it as, for example, X, because I wanted to showcase something. And remember what the definition is saying? It's saying that the product will be a linear combination of the columns of A using the corresponding entries of X as weights. So we have the columns of A, right here we're multiplying by the vector X, and this ends up being the linear combination of the columns of A. And this is why X has to have n entries. In other words, the vector X has to be an Rn, because we have n column vectors in A. So you have to have the same number of entries in X as you have columns in A. This is the true definition of matrix vector multiplication. When I say matrix vector multiplication, I really mean a matrix is on the left and a vector is on the right. And I mentioned this down below. Warning, for this product to be defined, the number of columns of A must be the same as the number of entries in the vector X. Now let's just go ahead and make up an example to see how this works, to make sure it jives with what we know. Let's pretend as though A times the vector X. Let's make A an interesting matrix. Now notice A here has 3 rows and 4 columns, so it's a 3 by 4 matrix. Now remember, we're going to create a linear combination of the column vectors of A. This is the first column vector, that's the second, the third, and the fourth, A1, A2, A3, A4. And therefore, we need to multiply by a vector X that has 4 entries. And I'll just make my entries easy. I originally had some zeros in there, but I decided that's probably not the best way to see this. So let's go ahead and see what that matrix vector multiplication is going to look like. Well, you're going to overlay this vector, you're going to pick it up and turn it on its side to showcase the columns that each entry in X are going to touch. For example, the entry 1 here in X will touch this very first column. The entry 3 will touch this second column. The entry -1 will touch the third column, and the entry of 2 will touch the fourth column. When I say touch, I mean it'll be the weight for that column. So let's go ahead and do this. Now we have a linear combination of vectors, and now you can actually do the scalar multiplications. Now you've done this enough that we can do this very quickly. And now we can actually use the definition of vector addition to add like entries. And there you have it. So that's a pretty decent example of matrix vector multiplication, interpreting this multiplication as making the entries of X the weights of each column vector in A. A couple notes before we leave this video. The first one is that the definition of the product of the matrix A and the vector X as a linear combination of the columns of A will be used very often. And it's probably a good idea to learn this definition in words as well as symbols. That is, oh, when I multiply the matrix A times a vector X, it's just a linear combination of the columns of the matrix A. The weights of that linear combination are the entries of X, specifically the corresponding entries of X. That's a good way to think about it. Symbolically, that was the previous page. The second note here is, while it is not wrong to write a scalar on the right side of a vector, for example, v times 3, well, first of all, I'm just going to interrupt my note here and say, that just looks weird. It's not wrong to write it that way, that just looks weird. You would never in algebra write x3. That looks weird. People would write instead 3x. So it's probably not a good idea to write your scalar multiples on the right-hand side of your vectors, nor should you do that on the sides of matrices when we get there. And so this kind of glues into our linear combination idea of the product of a matrix and a vector. While it's not wrong to write the scalar on the right side, it looks terrible. This is a number. That is a number. That is a number. It just doesn't look good. It's better to have those weights in front of the vectors. It just is common mathematical courtesy, I guess you could say. So the text I use follows the usual practice of writing a scalar on the left side of a vector. And in fact, I don't know of any text or any mathematician that would ever write a scalar on the right-hand side of a vector, a variable, a matrix, whatever. There's just no point to it. So please don't do that. Anyhow, that does it for this video. The whole point was really just to learn about matrix vector multiplication and make sure that you understand it in terms of a linear combination of the columns of the matrix A. I hope this was either helpful to you or a good review for you, and I hope to see you in another video. Have a great day and be a good human.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.